Hello students, let's study the case of cells in parallel combination. We shall derive equations to the equivalent EMF and equivalent internal resistance of the cells in parallel combination. To make the derivation, let's consider two non-identical cells with EMFs E1 and E2 and internal resistances R1 and R2 respectively. So we have the cells here connected between the points A and C, and we can understand both the terminals of the cells are keeping common connections separately, say one at A and the other pair at C. So they are found one over the other or one below the other. So we can understand the cells are in parallel combination. So as the cells are found across different branches and the cells are non-identical, they may be supplying different amounts of currents. So let's mark the amounts of currents to be I1 and I2. Which one goes towards the junction A will be combined to decide for the net current. So net current I here is marked as I1 plus I2. So we have to understand the current approaching the C, the junction also must be I, which is I1 plus I2, so that it can be splitted into I1 and I2 to respectively pass through the cell number 1 and 2. So let's begin with that equation. Say I equals I1 plus I2. Net current here is sum of individual currents. So now we are trying to draw an equivalent figure with an equivalent cell connected between the same two extreme terminals, say A and C. So this is a cell equivalent we consider for the reason even the same cell will be sending out a current of I, which is I1 plus I2. And E equivalent here is the EMF value for the equivalent cell. R equivalent by symbol here represents the corresponding internal resistance, such that E equivalent should be substituting the net EMF of the above two cells in parallel combination. Similarly, R equivalent also should be substituting the net internal resistance of the above two cells in parallel combination. Now we'll write VAC equations with respect to the branch containing cell number 1 and also cell number 2. So VAC, we do write like E1 minus IR1 with respect to the first cell, then E2 minus IR2, I2R2 with respect to the second cell. So equation number 1 has to be E1 minus I1R1. Equation number 2 is E2 minus I2R2. And these equations we are writing in terms of basic theories related to cell, which says terminal potential difference, that is E minus IR. Here the potential difference must be a terminal potential difference between the terminals of both the cells, for the reason cells are sending some currents out, or it's found a current drawn out of both the cells. So what potential difference now you will measure will be a terminal potential difference. That's why VAC is V otherwise, namely terminal potential difference. So VAC, each is a V by symbol and convenience. For convenience, VAC is by symbol V to write. So equations 1 and 2, which are V is equal to E1 minus I1 R1 and V is equal to E2 minus I2 R2. From equations 1 and 2, we will write for I1 and I2. Separate I1 and I2 respectively from equation number 1 and 2. And these values of I1 and I2 can be substituted in number 1. So I comes to be E1 minus V by R1 plus E2 minus V by R2. And from this equation do the simplification until you separate for V, the terminal potential difference between A and C. So for that we shall cross multiply. So it becomes I R1 R2 equals E1 minus V into R2 plus E2 minus V into R1. And the brackets in the right side can be opened. So E1 R2 minus V R2 plus E2 R1 minus V R1. And third and fourth terms in the right side, take common minus V out. So the kind of equation is E1 R2 plus E2 R1 minus V of R1 plus R2. We need to separate for V. So see that that particular term is transferred to the left side. Whatever there at the left side can be taken to right side too. So the change is V of R1 plus R2 comes to be equal to E1 R2 plus E2 R1 plus I R1 R2. Then R1 plus R2 can be taken for the right side. So V becomes whatever there at right side divided by R1 plus R2. So E1 R2 plus E2 R1 plus I R1 R2 divided by R1 plus R2. To get general expressions, what we try means this R1 by R2 to be divided between E terms and I terms, like that. So the equation is V, that's becoming E1 R2 plus E2 R1 divided by R1 plus R2 plus I R1 R2 divided by R1 plus R2. Leave it as equation number, say next, which is 3. So this is equation number 3. Now what our plan is to write VAC equation or V equation with respect to the second circuit or the equivalent circuit or equivalent figure in terms of equivalent cell. So that comes to be VAC, that is V itself equivalent to E equivalent minus I into R equivalent. So E minus I are formally in terms of corresponding parameters. Leave it as equation number 4. Now third and fourth equations to be compared. So similar terms can be equated. So when you compare, we get E equivalent to be E1 R2 plus E2 R1 divided by R1 plus R2. Then we can understand in place of R equivalent, it's found R1 R2 divided by R1 plus R2. So these are the equations to E equivalent and R equivalent. And R equivalent, if you look at, it is otherwise 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So this is the same equivalent equation to a resistance when you have two resistors R1 R2 in parallel combination. So cells, no matter in series or parallel, the equation to internal resistance to decide for the net will be the same as in how usually resistors come combined via series or parallel combination. So if you have one more cell here, what the equivalent resistance equation would be 1 by R equivalent, that is 1 by R1 plus 1 by R2 plus 1 by R3. Now we'll see for E equivalent. And E equivalent is of E1 R2 plus E2 R1 divided by R1 plus R2. But if you have one more cell to establish or to guess out an equation to E equivalent will be very tedious. So to keep E equivalent a general formula, what we do means dividing E equivalent equation by R equivalent. So we are doing that division here, E equivalent equation divided by R equivalent equation. So we can understand R1 plus R2 will be cancelled. Remaining will be E1 R2 plus E2 R1 divided by R1 R2. And when you split the terms in the right side, it comes to be E1 by R1 plus E2 by R2. This is number 6. E2 by R2, that is number 6. So E equivalent format here is E1 by R1 plus E2 by R2. So if we have one more cell, to write for such an equation is of no much difficulty. It could be of this form. So E equivalent by R equivalent, that is E1 by R1 plus E2 by R2 plus E3 by R3. If there is one more cell, what is it? It comes to be plus E4 by R4. And from here E equivalent can be separated like such a equation the right side multiplied by R equivalent. Because this is only E equivalent by R equivalent, from which if you want E equivalent means whatever in the right side, say E1 by R1 plus E2 by R2, the whole multiplied by R equivalent, you have to try. So E equivalent equation in general form is ready here. So R equivalent is say a form from 1 by R equivalent equals 1 by R1 plus 1 by R2 plus, like that. E equivalent will be R equivalent of E1 by R1 plus E2 by R2 plus E3 by R3, like that. Now different cases, let us see. So E equivalent equation is shown there. Now what if E2, the second cell of opposite order? If so, E2 can be taken as a negative. So the kind of equation will be this way. E equivalent can be R equivalent of E1 by R1 minus E2 by R2. So wherever cells in opposite order, corresponding potential can be a negative. Now the case of n numbers of non-identical cells, then E equivalent will be R equivalent of E1 by R1 plus E2 by R2 plus E3 by R3 plus E4 by R4 plus up to En by Rn. This is in case of n numbers of non-identical cells. And corresponding 1 by R equivalent equation can be this way. 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. Now third case. What if the cells identical up to n numbers? Identical and they are up to n numbers. So E equivalent will be identical and two numbers will see. From there we'll see the general equation of n numbers of cells. So identical and two cells. So E equivalent can be, R equivalent can be R by 2. How? 1 by R equivalent will be 1 by R plus 1 by R, which is 2 by R. From that R equivalent can be R by 2. So this is in case of two cells in parallel and identical. R equivalent is R by 2. So what about E equivalent? That is, from the equation say R equivalent of E by R plus E by R. Twice, because there are only two cells. That comes to be R equivalent, that is R by 2, substitute, into E by R plus E by R comes to be 2E by R. So we will get 2's cancelled, R's cancelled, left you E. So when you have identical cells in parallel combination, the net EMF must be E itself. Value of EMF of one of the cells. So if you have three identical cells in parallel, means E will be E itself, R equivalent will be R by 3. Let's see for that. Three identical cells. E equivalent will be E by R plus E by R plus E by R of R equivalent. And R equivalent is how much? 3 cells in parallel, each of similar internal resistances. So it comes to be R equivalent, 1 by R equivalent, that is 1 by R plus 1 by R plus 1 by R, which is 3 by R. So R equivalent can be R by 3, which we can substitute in the just previously written equation. So E equivalent comes to be, say that much is 3E by R multiplied by R equivalent, which is R by 3. Substitute. Cancel RR and 3. So as we discussed, the E equivalent equation must be E here for what is it, for a combination of 3 identical cells in parallel combination. R equivalent is R by 3. So what about 4 identical cells in parallel combination? E equivalent can be E itself, R equivalent can be R by n, R by 4. So n identical cells, then E equivalent can be again E. So what will be the number if cells are identical and in parallel combination? Equivalent EMF will be E itself, one of EMF values. R equivalent will be of the form R by n. If n is 3, R by 3, like that. Now we'll write equations to mixed grouping, where we can see a combination of both parallel and series among the cells of identical internal resistance and EMF. So identical cells we consider for convenience here also, such that in a branch of mixed combination we consider n numbers of identical cells with each of EMF E and internal resistance small r. So n numbers of identical cells in a branch. Such branches via parallel combination up to m number. There are m branches. In each we have n numbers of identical cells in series combination. So here this is the mixed combination of both series and parallel, we can understand. So every cell is of E and R as parameters. So inner branch, let's see what could be a net. Accordingly we will decide for the whole. Inner branch, when the cells are in series, net equivalent EMF will be N into E. R equivalent will be N into R. This is what we studied in the previous class about, say, series combination of cells. So inner branch, such a way equivalent EMF and internal resistance. Such m numbers of branches in parallel combination. So overall equivalent EMF E equivalent dash must be Ne itself, because when you have similar identical cells in parallel combination, net EMF will be one of those. One of those means in each branch we have Ne. So Ne itself will be now overall the EMF coming, even when you have Ne over m branches under parallel combination. Now R equivalent dash, which will be in each branch NR, that to be divided by the number of branches. So NR divided by M. So equations to equivalent EMF and internal resistance ready when you have many identical cells in a mixed combination of series and parallel way. And what about the current equation? When you have an external resistor of R connected here, I total equation, which will be always net voltage divided by net resistance. Net voltage means E equivalent dash. Net resistance means R plus R equivalent dash. So E equivalent dash is Ne, substitute that, divided by net resistance, the external resistor plus the net internal resistance over the branches, over the cells, that is R dash equivalent. R dash equivalent is NR by M. So we do a division between total voltage and total resistance to decide for total current. And when you reduce the equation, or it is a form MNE divided by MR plus NR. So here again you can see the case of what if capital R 0, what if small r 0. Keep the equations ready for currents under those conditions. Now what we will write means to write for current equation for the parallel combination of total currents equation. For the parallel combination alone we will write that comes to be E total by R total. So E equivalent divided by R plus R equivalent. Capital R here is the external resistor which is connected across the cells in parallel combination. We are writing for identical cells of n amperes under parallel combination. So the kind of equation will be E equivalent by R plus R equivalent. E equivalent will be E itself, because cells are of E as an EMF such that the cells are in parallel combination. So net EMF, we just studied that could be E only, one of EMFs. So E divided by total resistance. First we will write for two cells, so R plus R by 2. 2E by 2R plus R. That's an equation here for two identical cells. We did for two identical cells. So the kind of equation of I total will be 2E divided by 2R plus small r. Small r means resistance to each cell. E means EMF to each cell. Capital R is resistance which is externally connected. Now, what in case of n numbers of identical cells in parallel? The only difference will be instead of 2 as a number, n will come. So we'll write I total to be, say, E total divided by resistance total. E total means E itself. Resistance total means R plus R by N. On reduction we may get NE by NR plus R. This is I total in case of n identical cells in parallel combination alone. And from here we can separate for I maximum, which is when capital R is 0. That is NE by small r. With capital R 0, no external resistance is connected. By then the total current will be maximum here, which is NE by R. So this we are speaking for n identical cells in parallel combination. So that's it. Thank you.